Okay, hello. Looks like we have our technical difficulty solved. And welcome again to this press conference on surprising findings in Greenland's melt dynamics. Katie Human, who's the Director of Communications at CERES, she'll explain the acronym, at the University of Colorado in Boulder, will introduce the speakers.
Thanks, Peter, and thanks to you guys for fixing our technical glitches. I'm with CERES, the Cooperative Institute for Research in Environmental Sciences, which is a partnership of the University of Colorado Boulder and NOAA. And for the next half an hour, you're going to get a series of interesting discoveries about Greenland's meltwater. This is a fraction, of course, of what you can hear about Greenland if you go to scientific sections at AGU, and I would encourage you guys to go to some of the sessions that we'll post on the final slide here today. Because we're a little slow in starting, I'm going to go ahead and introduce Anders Bjork from the Natural History Museum of Denmark, Laura Koenig, who just recently left NASA Goddard for CERES. She's at the National Snow and Ice Data Center now, which is part of CERES. Rick Forrester from the University of Utah, and please note that his name only has one E, not two, like on our press release. And Mike McFerrin, who is a graduate student at the University of Colorado Boulder and also part of CERES. Anders, thanks. You can do it.
All right. Yeah, thank you. So this first talk stands out a little bit from the others, as we're going to go quite some years back in time, about 110 years, in Central East Greenland, where we will look at some local glacier changes. As you can see on this picture, the glaciers of Central East Greenland, they have really changed in the last 110 years. What we can see is the extent they had after the Little Ice Age. And since then, they have really retreated, and that's what we'll look into. If we look at the temperature, we can see that the last about 20 years, we have had quite a significant temperature increase, about 1.3 degrees per decade. But there was also an equal large increase in temperature in the 20s and 30s, and that was a little more steep increase, about 2 degrees per decade. But the maximum temperatures didn't get to the same level as they had now. But what's really interesting about this study and the data that I will show you now is that we can, for the first time, look at what happened after the Little Ice Age and see the retreat rates of glaciers, because we have some really interesting and amazing data from early photographs from Greenland. It's really a remarkable story of these photographs came to be. And the story starts here in the office of Adolf Høhl. He was the director of the Norwegian Svalbard investigations, and he convinced the Norwegian officials to actually occupy part of East Greenland in the early 30s. East Greenland was almost a no man's land at the time. Denmark believed they had the control of the region, so they were quite surprised when Norway occupied this part of Greenland. And as a response, Denmark started to make some really large-scale scientific investigations, and so did Norway. They found out pretty quickly that this dispute was to be settled in the Court of Hague. And the best weapon in this battle would be to have a lot of scientific investigations in the area. And one way of doing that was to map the land. It wasn't mapped very well at the time, and the technology of that time was airplanes and mapping from the sky. So they set up really big campaigns to map Greenland from the sky. Both Danish pilots from the Danish Navy and pilots hired in from Germany to photograph from the Norwegians. Here we see some of the pilots. These were Danish pilots. In the middle is a geologist who mapped the geology from the land. And for the Danish geologists, this was really a big challenge. They came from a flat country where the highest peaks are about 500 feet. And suddenly they were flying around 11,000 meters, minus 20 degrees temperatures, and a lot of difficult challenges that they were not used to. It was exactly the same for the Norwegians. They had another attitude towards it. They used some planes that were taking off from land, where the Danes were using planes that were taking off from the water. But all in all, they managed to take a lot of really amazing photographs. And here we see one example. That is from Fenris Glacier in southeast Greenland. And you can see the change that has occurred since, that's on the left-hand side, you see a picture from 32. And on the right-hand side is from last year. This glacier has retreated about 5 kilometers. And here, it's quite remarkable all what they managed to do in 4 years. In red, we see the Danish flights, and in green, the Norwegian flights. And in yellow is the area that I will look into now. Just for comparison, here we have the ice bridge flights. Oh, sorry. Here we have the ice bridge flights from 2003 till 13. They have also flown quite a lot. And the next 3 talks will talk about data from these ice bridge flights. Another interesting thing is that Louise Boyd, an American explorer, she's a local girl from Marin County. She went into this area in the mid-30s and recorded lots of photographs and made some extraordinary maps of glaciers in Greenland. She actually made some of the best maps that we have of glaciers. And we've also used her photos in this work. So we have 2 areas where we have rising temperatures, and I will just briefly show you the results from these 2 areas. There's a lot of circles here, and they are red. Red means that the glacier is retreating, and green means that the glacier is advancing, and the bigger circle, the more retreat or advance. And this was quite surprising to us to see the magnitude of retreat following the Little Ice Age. The Little Ice Age ended at around 1910, and the retreat rate, average retreat rate is about 30 meters per year. Compared to now, we are looking at something like 10 meters per year. So this is a really rapid retreat following the Little Ice Age. We also looked at the intervening period, and that also brought a surprise to us. From the year 1990 to 2000, if you remember the temperature curve, we had rising temperatures. But we also get a lot of glaciers that are growing, and they are growing in the north and close to the coast. And this was quite a surprise to us. When we look more into it, we have a rising temperature, and we must have some changes in accumulation. And these changes in accumulation fits extremely well with the positive NAO index, NAO index. And this is one of the findings of the more recent glaciology that we can take from this study. Yeah. So we have, all in all, a massive meltdown following the Little Ice Age, and then we have a group of glaciers in East Greenland that are extremely sensitive to changes in climate and in temperature. Yes, and with that, I'll give the word to Laura Koenig and take some questions afterwards. Thank you.
Great. Thank you, Anders. Now I'm going to transition a bit to talk about Greenland's water. And I want to start by showing these 2 pictures. Now, in the past studies, most of the most of the sea level rise from Greenland came from ice discharge. Now, in the past decade, this has switched, where it's no longer these giant icebergs calving off, but the majority of the contributions to sea level from Greenland is coming from surface melt. So it's coming from a warming of the surface, and this is a bit of a paradigm shift that probably started around 2006 to 2009. Now, at about this same time frame, Icebridge started monitoring the Greenland ice sheet. Now, Icebridge is an airborne campaign, a NASA airborne campaign, and what you see here in green is a laser altimeter. It measures the surface of the ice sheet, and in the gray and black are radars, and some look at the near surface of the ice sheets, which is the gray, and then the black line we'll see all the way to the bed of the ice sheet. So here as we zoom in, I'm going to be talking about this gray line, these radars that peer into the ice sheet just in the near surface. And what Icebridge does for the first time, starting in 2009, gave us a 3-dimensional view of the ice sheet. We can see how the surface is changing, as well as what happens with the radars as we peer within the ice sheet. Now, as I was on a flight, one of the radars was operating. This was in 2010, and again, it was peering beneath the ice sheet. And what you see here on the right are the radar echograms. And the radar operator called me over and said, hey, there's this bright return that is coming from the subsurface. And we were over where the superglacial lakes, the lakes on the surface of the ice sheet form. And I said, oh, well, that's probably just the lake, the ice from the top of the lake. Well, we were just looking at one radar then. That evening, we went home, back to the camp, and we mapped where we saw those returns. We saw that, of course, they did line up with where the lakes had formed the previous summer. But there was another surprising finding. Here we're looking at all 4 of the radars on board. So they see in the near surface all the way down to the bed. And all of the radars were showing this attenuation. And that showed us that it was not just an ice lens, it was actually water that was being retained in these lakes. So here's a schematic view of what's happening in what we're calling buried lakes. The winter snow falls, and these lakes that had formed on the surface of the ice sheet are now retaining water, and they're retaining water year-round, giving a year-round hydrologic cycle of the ice sheet. Now, here's a life cycle of a buried lake. Now, if you are a lake that forms on the surface of the Greenland ice sheet, there's kind of 3 things that can happen to you. You can drain to the bed or overflow to the next lake. You could refreeze completely in the winter, or now we know that you could also remain and persist through the next winter season. So here's June 2nd. The lake is starting to form just as the ice sheet starts to, the snow on the ice sheet starts to melt. Around July 4th, it's a very full lake. You can see a little ice floating still on top of it. Somewhere between July and August, part of this lake did drain, and this red line is where Ice Bridge overflew it the next spring. And in the next spring, here's what the surface looked like in the center. You can see that there's maybe a little bit of an edge, but it's basically white, and hidden below this surface, what the radar showed us is that there was still this buried lake. So the radars are showing us that there's a lot of buried water hidden to us if we're just looking at the surface, but the radars can detect it. And what this water is really doing is it's priming the pump for the next season. So all of these blue dots are where we have mapped these buried lakes. The lakes are extensive in area, but they are quite small in the volume of water. This is not a large amount of water that it's retaining, but locally it will warm the ice sheet. And this, let me run the video again. This video is actually showing the lakes are mainly along the west coast, and as we go into Rick and Mike's talk, you'll see that their data is also displayed on this. And what this is starting to show us is a picture of Greenland, where all around the perimeter of Greenland now, we're having a lot of water. For the stability of an ice sheet, water is not a good thing to have, and especially persisting year-round. It will warm the ice. So again, these buried lakes, they will warm locally, but it's not a large volume of water. Now Rick is actually going to talk about the Greenland aquifer, which is an extensive amount of subsurface water, which is also a voluminous amount of subsurface water.
All right, thanks, Laura. Yes, I'm going to talk now about another surprising way that the Greenland stores water that we didn't realize. And I'm going to give you a little bit of background first before I go into some of the new findings we've had. And as part of that background, I'm going to show a short video of the first time that the aquifer, the Greenland aquifer, was actually drilled into. I'll give you a little bit of background about this. This is going to show a core coming up from about 25 meters depth in the ice sheet. And typically this process, we bring these cores up and then we bring them back to the laboratory and we date them and we measure how much snow is accumulated. So typically as you're bringing these cores up, they're typically dry, there's no water in them, and it tends to be a boring process on the surface. We bring them up and then we put them in tubes and ship them off to the labs. But this is the one that was the one that first actually penetrated the ice sheet. So I'm going to show you that. If, whoops, maybe. Do I click on it? Okay. Okay, so actually you can see here water just pouring out of this core. So keep in mind, this is April 1st in Greenland. Air temperatures are minus 20 degrees C. Melt on the surface doesn't occur for another 2 months in this area. This is long before any surface melt, so we know that the water pouring out of this core that was extracted from 25 meters below the surface definitely persisted throughout the winter. Okay, so this was a new finding. And what I want to do is give you a little bit more background about what we ended up doing with this, this discovery. This was work that was published about a year ago. The team that was there in the field had a ground-penetrating radar with them. In fact, that night they went in the tent once they hit this water layer, and they processed the data initially and saw this really bright reflecting horizon here. And this is actually the top of the aquifer. The depth corresponded exactly to 25 meters where they drilled in that location. So they knew they could map it with a ground-penetrating radar. Now, fortunately, NASA, just actually 11 days prior to the traverse here, shown in green, overflew with one of the radars that Laura was talking about that looks at the near surface, and it can also map out the top of this aquifer. So then we took all the data, all these gray lines on here are flight lines from NASA's Operation Ice Bridge, and then we mapped all the locations where we saw this bright reflector that we corresponded with the aquifer, and these are these purple regions down in here, mostly concentrated in the south and the southeast. Okay? So then we also collaborated with colleagues from the Netherlands, and they had a climate model that was used to estimate Greenland surface mass balance. And they had what they thought was an error in their model for years. It kept predicting water being retained throughout the winter. And they thought this was an error until we compared data at these colored areas here are where their map was predicting water persisting. And now the dots, we turned them black, are the areas where we observed the aquifer existing. So these lined up really well where we had ice bridge data. Okay? Their model also predicted liquid water persisting a little bit farther north in these areas here, but we didn't have ice bridge data here in 2011. Okay, so now I'm going to transition on to our recent findings. And one of those is we've added 2 more years worth of ice bridge data. Okay, so in red was the 2011 data. That was the data I was showing you already. But we've added the blue and the green, and those are the 2 additional years of ice bridge data. And what we're finding is further agreement with the model. These areas a little bit farther north on the east coast here where the model is showing water retained. We're seeing it here with the ice bridge data, and also way up here in the very northwest corner, seeing presence of the aquifer. So what we're able to do now with 3 years worth of data, and we've got a 4th year that's already been acquired but hasn't been processed yet, we're able to start to build a picture of all of the locations where the aquifer exists. But it's, as you can see, it's taken us multiple years to get to all those places. So in addition to filling out our map of where the aquifer is, additional years where some places we have repeat flight lines. So the airplanes flying in the exact same place. And what we're seeing here, these are 3 years over a segment here near Helheim Glacier. And we're seeing the first 2 years consistent returns, and then this 2013, we're seeing a significant change. In fact, it looks like we're losing the presence of the aquifer down here at the lower elevations. And this is an area where crevasses begin. Okay, so one hypothesis that maybe we're getting some drainage of the aquifer into the crevasses. Okay, so we haven't quite figured out the exact process here, but the point is that we're seeing changes in the aquifer. So it points out that we need to be continually monitoring and looking for the details. Okay, in fact, there's a poster by Clement Liège on Friday morning with more details on this finding. Hey, another finding we have is we now have a technique where we can map the aquifer not just from an airplane, but actually from a satellite, from space. And this gives us a big advantage of being able to take a snapshot in 1 year, get the entire presence of the aquifer without having to piece it together with additional flight lines every year. And you'll notice the places where we're mapping it from space corresponds really well with the observations we're getting from the ice bridge data. I'm not going to go into too much more detail on this because we're planning on submitting this to Nature Geoscience in the near future, but I will direct you to Julie Miller's poster tomorrow morning about this. The other important aspect here is now we can monitor in the future with satellite data. We can also now go back in the past. There's archived data of a similar satellite. We believe we can go back to the early 1990s and look for the evolution of the aquifer system. And I'm going to end now with just talking about our future plans. We're going back into the field in April of 2015 with a whole new set of tools to further characterize the aquifer. We're going to use seismic refraction imaging, some nuclear magnetic resonance at the surface to hopefully estimate the volume directly, and we're going to take a whole suite of groundwater measurement techniques to date the water, try to figure out how long it's been there, and also do some measurements on the flow of the water within the aquifer system itself. Okay. So I'll hand it over to Mike now, who's going to talk to you about another aspect of water in the ice sheet. Yeah.
So my portion of the talk is actually what's happening to meltwater that's not staying liquid through the winter. So mine actually starts as a story. It is a story. In 2012, we were in a spot in the southwest Greenland ice sheet that's, and it's in a region called the percolation zone, where we have fern, that's this porous, crusty snow that you see in the core on the left there, interspersed with these layers of ice that are refrozen from meltwater that melted at the surface and refroze into these lenses. And this is what we expected to find as we were drilling these holes and pulling up these cores, is we expected to find lots of fern with little ice layers interspersed throughout it. What we ended up getting, as soon as we got about a meter or two below the surface, was core after core of solid ice, just pulling up meter after meter for nearly 5 meters straight of just ice after ice after ice, and it was way more ice than we expected there. And we knew what was causing this ice. We knew at that time, spring 2012, we knew that 2010 had been a huge melt year. 2007 had been a big melt year. We had several of these large melt years ahead of time that had generated more meltwater and must have refrozen into lots and lots of ice below the surface. And we sat around in camp wondering how much room there was still down there. This is a porous sponge of fern that can soak up meltwater, but the sponge was filling up fast, and we wondered how many more big melt years would it take for there to just be no more room for the water to go anywhere, and it would have to start running off. And we got an answer very, very quickly. That summer in 2012 turned out to be a record-breaking melt summer that blew out the 2010 record. And CanU, the location of our camp, is there noted in the middle of the image, and this is a processed color-enhanced Landsat 7 image that shows meltwater percolating from very near where our camp was, running off westward towards the edge of the ice. And nobody had seen meltwater running off the ice from this high in this region of the ice sheet before. And this was, we knew we had valuable data, and we just accidentally timed it perfectly there. So let me back up. In order to really tell the story right, I'm going to rely on a brief animation about the zones of the ice sheet. It's Glaciology 101. At the top of the ice sheet is what we call the dry snow zone. Snow accumulates in the winter, and then it doesn't really melt in the summer. It doesn't get hot enough. It just settles down and compacts onto the layers beneath it. At the opposite end, down at the margin of the ice sheet, we have what we call the ablation zone. It's bare ice down there. That's where you get the pretty pictures of crevasses and everything. Still accumulates in the winter, but it's warm enough in the summer that it melts away completely. And the meltwater that does get generated will run off towards the coast, and that feeds the rivers that flow out from Greenland in all directions. But there's a vast region in between those two called the percolation zone, where snow accumulates in the winter still, but then it just partially melts in the summer. And that melt percolates down and refreezes into these ice layers that you saw in those cores before. But if you start increasing the amount of melt, then more meltwater gets generated, and it forms more and more ice layers and intermix with the layers in between, and you start getting more and more lenses forming. And if you keep this up for long enough, you start getting more and more melt, those lenses will eventually start merging together, and you'll start getting very thick, continuous lenses in the undersurface. And once you get this, once they're thick enough and continuous enough, then if you get another big melt summer, it starts running off. It has nowhere else to go, and that's what we saw in 2012. And this is a potential mechanism for melt and runoff to migrate quickly up the ice sheet. So in May, this is actually a picture of us standing over the Watson River, which runs through Kangerlussuaq, Greenland, in mid-May, when the water's low. Melt hasn't really kicked in yet in the river. But, and this is actually the same drainage of where our camp was that flows into this river. And in that summer of 2012, the river flooded pretty much the entire month of July. This is actually after the peak flow. If you do a YouTube search for Watson River flooding in Greenland, you get a lot of very dramatic images of those bridge abutments washing out and a tractor getting washed away. You can find that on YouTube. But that bridge had stood there for approximately 56 years and had never been touched by the river. And at that point, this was definitely record flooding. And this is even, again, this is courtesy of Marco Tedesco at City University in New York. But this was an incredible amount of meltwater. So we knew where at least some of that water was coming from. We returned the following year, in 2013, with a ground-penetrating radar dragged by a snowmobile to map out these ice layers. And we found that where our camp was, which is approximately where the runoff line was here, the long-term saturation zone, where for long periods of time it's melted down to bare ice and refrozen into solid ice. That's, if you drill down through here, you'd find solid ice almost the whole way down. Runoff was occurring nearly 20 kilometers inland from that. And the more surprising finding to us was that even 20 kilometers up from where we saw runoff in 2012, there's still perched thick ice layers under the surface there, even where added runoff isn't occurring yet. And it's hard to say exactly how quickly these perched layers could play a role in runoff in the near future. And we chose the specific line we did for this particular radar transect because it underflew a NASA Ice Bridge mission, actually the same frequency radar that Rick was using for mapping the fern aquifers. We can see the thickest of these ice layers. It's coarser resolution. I can't make out the fine stuff. The thickest of these ice layers show up clearly in the Ice Bridge radar, and we get a very good idea about where on the ice sheet these things are happening. And the areas highlighted in pink here are where we're seeing massive perched ice layers, about 1.5 meters thick or more, perched above more porous fern layers around the edge of the ice sheet. And although it doesn't stay liquid throughout the winter like Laura and Rick's focus areas do, it is, at least some of these regions are, we're seeing contributing to runoff, a larger runoff basin from the ice sheet. And that's, I've got a more detailed map of this on my poster session tomorrow, which leads me into actually all of our talks and poster sessions. If you didn't make Anders' talk this morning, you missed a pretty good one. But we've got, Rick and I have posters tomorrow, and Laura has a talk Friday morning that go into more detail about each of these processes we're talking about here. So I believe that's it. I think we're open to question and answer now.
Okay, thank you, speakers. And we're open, as you said, to question and answer. And questions we welcome questions from members of the press only. So do any reporters here have questions? And please state your name and your affiliation.
Hi, my name's David Appel. I'm with Yale Climate Connections. Is there any evidence that these lakes existed before 1990?
So this is the first time that we've had the radars that see with really fine resolution. So we know from 2009 to 2013, there's one report, written report, in 1992 of multiple ice lenses. So they felt like a lake drained throughout the winter. But that's the only written data. There is, as Rick actually talked about, some archived radar data that we'll need to go back and look at. But as of now, there was just one report, and they think it drained during the winter, didn't persist.
And I was just wondering, how was this year's melt compared to 2012?
You talking about 2014 melt?
Yeah, this year, yeah.
Not as dramatic as 2012. It was, I mean, it depends what baseline you're comparing it to. It was fairly average for recent years. It was warmer, I believe, and you guys could verify this, but warmer than slightly warmer than the long-term average, at least the 30-year average, but it wasn't a tremendous year in either direction.
Paul Doherty from the Exploratorium. How do you date water?
There's groundwater techniques to use isotope chemical analysis to try to get at it, and they can usually get within a few years. And these are established techniques that have been used for terrestrial groundwater systems.
Other questions?
So other than short-term effects, like when you get a big runoff on here, how does this affect like a medium-term rate of loss of ice from Greenland? That is it just coming off in a big slug this year rather than next year, or is the whole thing melting faster because of these water effects?
Well, I think a simple way to say this, again, is that the more water we see persisting year-round means that the ice sheet is warming, not only from the surface, but also internally as it percolates down. So as we start to include these processes in the model, we would assume that in the medium range, the projections for sea level could go up. Now, the one Rick's, and I'll confuse that just a little bit, but with Rick's work with the aquifer can actually store large amounts of water, but we need to understand the mechanisms for how that releases. So that could help mitigate, but at some point it's warming and that water has to release, and we don't know what time frame that would be on.
It's worth mentioning that a lot of these results are new enough that we're still trying to wrap our heads around and collaborate data sets and everything else to try and pin down the mid and longer term results, but there's a whole lot more that we don't know than we do know at the moment.
And that's kind of one of the things we're finding, I think, is that there are still discoveries to be made. There are processes and conditions in the ice sheet that we didn't know existed just a few years ago. And the actual process of how this water gets to the ocean ultimately is our question, because that's how it affects sea level rise. Those pathways aren't completely understood at this point.
Other questions? Any questions from the chat?
Yeah. We have a question from Bas Den Haan, freelance. How does the water in these buried lakes manage to stay liquid under the ice for a whole winter?
Yes, so that's a good question, because the air temperatures would be quite cold. What's happening, just like, say, a lake in Vermont or Minnesota, where you are getting both an insulative layer of ice on the surface of the lake, as well as insulation from the snow that falls on top. So you have snow, and then ice, and then water. So the water has to be deep enough at the end of the summer, probably, to persist through the winter.
Another question from the chat. This is from Pete Spots from the Christian Science Monitor. How do the aquifers form? The same process that forms the lakes, or something different?
Yeah, so they kind of begin with the same process, which is surface melt. But what's happening different with the aquifers is that the water is percolating, kind of dripping its way down into last year's snowfall, and then filling the gaps in between the ice grains of last year's snowfall, and then it's worked its way down into older and older snow that actually is then called firn. And then in a similar way, they're persisting throughout the winter as the lakes, is because they're getting buried pretty quickly by very thick, up to 3 to 5 meters of snow that accumulates, and that's thermally insulating, kind of protecting the relatively warm water from the very cold air temperatures throughout the rest of the winter.
Any other questions here in the room?
So you say that you think that there was a paradigm shift that started around 2006 to 2009. Do you have any idea why that shift happened?
So it's probably directly related to the warming, so the atmospheric warming in the regions, and we know that the temperatures over Greenland are warming. So as that warms, we put more warmth onto the surface of the ice sheet to melt the surface. Previous to that, it was the ice dynamics. So it's probably directly related to warming.
Okay. Please identify yourselves, by the way, when you ask a question by name and affiliation.
Paul Doherty again, Exploratorium. So in one of the earlier images you had advancing and retreating glaciers. And I know that the difference between temperate and Arctic glaciers, what's going on?
Yeah, so in this figure that I showed you where we had both advancing and retreating glaciers, the glaciers that were advancing were close to the coast where the precipitation is much higher than closer to the ice sheet. There's about 150 kilometers difference from these areas. And the snowfall or the accumulation has really increased a lot in this period, and that is what is driving the glaciers to grow in a period of time where temperatures are increasing.
Any further questions from the chat?
I just wanted to let folks know that all the animations and visuals, and most of the visuals, will be available on series channels on Flickr and YouTube. Let me know if you have any questions about obtaining them, and thanks for your time.